Okay, for question number 3, what you got here is your probability question. This is binomial. The reason is we are talking, there's your trigger word at least one. So B, binary, they get the gift card or they don't. I, each selection's independent. N is 52. And S is 1 out of 200. And this is binomial. And you'll see the same thing on his solution here. So as far as at least one, you could do 1 minus the probability of none. You could do it this way, or you could do 1 minus binomial CDF of n equals 52, p equals 1 out of 200, x equals 0. At least one, so we're just subtracting away 0 to get this probability of about 23% for that second part. On page 2, calculate and interpret the expected value. This is binomial, so it's just n times p, which you'll notice he did here. N times p, expected value just means find the mean, 0.26. And this is over the long run. So if they were here for a long time, on average, they'd get 0.26 gift cards per year. All right, moving on to part C. Suppose that Agatha never received a gift card for the 52. Okay, so you want to use your probability to answer this question. The probability of not getting a gift card would be this 77%, because the probability that you get at least one gift card is 23%. So it doesn't seem that unusual at all, because there's a 77% chance that an employee is not going to get a gift card. So to me, if you're talking about binomial here and you have either N or P, or you've done some work with bins but didn't say binomial, that would be a partially correct. I wonder if they'll clump 1 and 2 together, or these will be separate in the grading. I guess I'm not certain. Part 2, if you forgot to subtract away and you found the probability of maybe exactly 1 or exactly 0, maybe that's a partial. Part B, what I'm going to expect here is that there's 2 parts, the actual calculation and the interpretation. If you have one of those 2 correct, it would be partial. And you'd have to say something like on average or in the long run. And then for part C, know and use your probability to determine why or argue why it's not unusual in context. So again, this might have 3 or 4 parts. If it has 4 parts, E's are worth a point, P's are worth a half a point, and you can figure out different pathways to get to 2. Okay, question 4, convincing statistical evidence. Here is your significance test. So this is just a nice one proportion Z test. So your state step, P is the true proportion of customers who place an order after getting a coupon, 40%, greater than 40%. And then for the plan, so what they're going to do is they're going to group your hypotheses with your name, that you have one proportion Z test or one sample Z test. Those will be an EP or I on its own. Then the next EP or I is going to be the rest of your plan step and your do step. So there's a random sample of 90. 90 is less than 10% of all customers. Now here's where things get tricky. With the large counts condition, you do not use the 38. It's 90 times the claim, so 36 and 54. That's something that a lot of students might forget, so that would knock you down to a partial. Your test statistic, depending on rounding and stuff, is going to be around Z equals 0.43, and your p-value around 33%. So they're going to grade your random, independence, large counts, the test statistic, and p-value all together. So if you have a slight mistake here, like I mentioned with the large counts, I think that's going to be a partial correct, or something else, small mistake. And then the conclude is going to get its own EP or I. Because the p-value is greater than that, we fail to reject. There is not convincing evidence that the true proportion is over 40%. So now part B gets into talking about, okay, based on your conclusion, which error could have been made, and interpret the consequence of the error in context. So here, because we failed to reject the null, that would be a type 2 error. Now, if hypothetically you somehow rejected the null, then you would have wanted to say a type 1 error here. That would be convincing evidence, and that would be consistent. So here, type 2 error, not finding convincing evidence that the manager's belief was correct. The consequence would be the manager doesn't send the coupon out, but as a result, they're losing out on potential sales. So that part B is going to be given EP or I. I think if you have the right error, but your consequence is a little not well explained, that would be a partial correct. So you have 4 parts here. So E's are worth a point, P's are worth a half a point. Hopefully you found a path to get to at least a 2 on this one. Okay, question 5. This looks like it's a test, and they do start to get to that in part C. So suppose one teen is randomly selected from each city's sample, and they want to know the likelihood of a teen from Baltimore who consumed a soft drink is less than the likelihood of selecting a teen from one of the other 2 cities who consumed a soft drink because there's a lower number of teens. Is the claim correct? When you look at the data, you're going to find it is not. Because given Baltimore, there's 80%, given Detroit, given San Diego, there is a lower percentage here. So Baltimore is actually the highest. The reason being is because the sample size here was the smallest, and this represents the largest percentage. So it turns out that this probability is actually higher. So I think if you said incorrect and you had some justification, but it was weak, that would be a partially correct. I don't know anything else that would be a partial correct. All right, so let's look on to the next part. Part B, consider the values in the table, construct a segmented bar graph. So this is just using conditional probabilities. C graph. Oh, he must have put it on the graph, but I don't have that graph. So essentially what you're going to do is you're going to take Baltimore 727 out of 904, 177 out of 904. So Baltimore was like, where is the percentages we just got? It would be split into 80% and 20%. Detroit would be split into 74% and 26%. And then San Diego would be 65 and 35. So that's what's going to show up on the conditional probabilities as far as the segmented bar graphs. Everything's labeled for you. That was really nice. So that's what that part's going to be. Which city had the smallest proportion of teens who consumed a soft drink in the previous week? And we already kind of did that work in part A, potentially. It would be San Diego. So I think part B is going to be just graded all together. And partially correct would be, I think most of the grading is going to come from section 1. Section 2 is just going to be that conditional probability and the proportion, the conditional probability from San Diego, and showing that that's about 65%. So maybe that's enough to weight it equally. So if you have this correct for graph with your percentages and part 2 is incorrect, I think that's a partial, or vice versa partial. So I think those are going to be clumped together. Part C, now we're talking about consider the inference procedure that is appropriate for investigating whether there's a difference among the 3 cities. Okay, if there's a difference among the 3 cities in the proportion, now we have 3 cities. So 1 proportion test is out, 2 proportion test is out. We're looking at chi-squared. We're looking at the whole distribution. Now what they've done is they took a random sample from each city, random samples. So this is a chi-squared test of homogeneity. That would be the procedure. And then the hypothesis would be, the null hypothesis would be that there is no difference in the distribution of soft drink consumption among the 3 cities. And the alternative would be that there is a difference in the distribution of soft drink consumption in the 3 cities. Okay, so you can see his solutions. All right, moving on to the last question, your investigative task. Okay, so you have 2 box plots, compare the distributions. Hopefully you were thinking Visco here and you used comparative statements. So in terms of, let's start with center. we have a much smaller attendance, lower center of attendance at the old stadium versus the new. You could specifically talk about the median being 16,000 compared to about 25,000. That's that variability. There's greater variation in the attendance at the new stadium than the smaller stadium or the old stadium. Not by a lot, but you could reference the IQR being about 4,000 versus maybe about 3,500, or the range being larger. As far as the shapes go, the distribution for the new stadium is skewed to the lower value, so skewed to the left. And the old stadium is about roughly symmetric, so they differ in shape. Any mention of modes is extraneous. If you said something about normally distributed, like that's going to be off. You're going to lose credit there. Neither distribution has any outliers. So that's what I'd be thinking about. Oh, there's his graph. Okay. Median attendance higher in the new stadium than the old. The attendance in the new stadium is skewed left, roughly symmetric in the old. There's more variability in the new stadium than the old. You don't have to include concrete values. There's no outliers. Okay, so I'd say if you correctly have comparative words, you're going to have, if you have 2 out of these 3, that's going to be a partial. 3 out of 3 is going to be essentially correct. 1 or 0, I think, is going to be incorrect. All right, let's move on to part B. Now we have the scatter plot for average attendance versus year. Compare the trends in average attendance over time between the old and the new stadiums over time. Okay, so the trend in attendance at the old stadium appears to be flat, around 16,000, with considerable variability each year. The new stadium has been increasing significantly with time. The association is strong, linear, and positive. So I'm kind of on the same line of what he's saying. I think I'd be thinking a little more DOFs, like there is a moderately, we're comparing. So the association with the new stadium when it comes to attendance is stronger than the association of the old stadium. It's more positive, where the other one's more kind of slope towards 0, strength, direction. And it's more linear. So that would be my comparison. I think as far as this grading goes, it's going to be very similar. Did you correctly compare strength, direction, and form? I don't know if they're both kind of linear, so I don't know about the form piece, and really no mention of outliers. So maybe just strength and direction. Are you comparing those correctly using comparative words in context? All right, moving on to part C. Now we have different scatter plots. We have graph 1 is the new stadium, number of games won, and average attendance. Graph 2 scatter plot is now old stadium and new stadium. Okay. So graph 1 shows the average attendance versus number of games won for each year. Describe the relationship between the variables. There's a strong, positive, linear association between number of games won and average attendance. In general, as number of games won goes up, so does the average attendance. Part 2, graph 2 shows the same information but indicates an old and new stadium. Does graph 2 suggest that the rate at which attendance changes as the number of games won increases is different in the new stadium compared to the old stadium? To me, no. All of these points fall essentially on what would be the same line of best fit. So the old stadium and the new stadium both have the same constant rate of change. That would be my argument. No, considering just the old stadium or just the new stadium would have similar slopes. Okay, so I think part C is going to get its own grade. Each part is going to be like part of it. So if you have one part correct, that's going to be a partial. Both parts correct would be essential. And then you could go from there. Okay, part D, or letter D. Let me go back to the question. Consider the 3 variables: number of games won, year, stadium. Based on the graphs, explain how one of those variables could be a confounding variable in the relationship between average attendance and the other 2 variables. So which one of these could be a confounding variable? Remember, confounding variables, a variable other than what you're investigating that influences your response. So going back to the graphs, Your response variable is the average attendance, and then we have year and number of games won. So you can see here, number of games won didn't really have a difference between the old and the new stadium, where it looks like the year did. So if we go to his solutions here, the number of wins would be a confounding variable for attendance versus stadium versus year. Well, it's true that the team had much greater attendance in the new stadium than the old. All of their seasons with more than 85 wins occurred in the new stadium. In addition, they had one season with only 80 wins, and its attendance was similar. Okay, so he's arguing that it's the number of wins because the attendance is strongly correlated with winning. And all but one season, the new stadium had more wins than all the seasons and every season since 2000. The association between stadium and a year of attendance is confounded with the number of wins that season. Okay, that's not exactly where I was going, but I think he is right, and I think I am wrong. So the number of games won, you could see a big discrepancy between the two. Okay, so that in and of itself is going to get an EP or I. I don't think just choosing the right variable on its own is going to get you a partial. I think you're going to have the right variable and some kind of weak explanation. So you have 4 parts, part A, part B, and then C and D. So I think if you can at least get a point, if you go partial on part A and B, that's going to get you to a point. So hopefully you're able to earn a point on this.